Hello everyone, welcome to our channel Mathematics Pathshala. Now I would like to announce a good news for you that we have started to add solving GATE questions in our channel. A student qualified in GATE exam will get call from various IITs for PhD entrance, and also they can take admission in MTech by qualifying GATE exam. Considering the importance, we started solving GATE 2024 mathematics question onwards. In this video, we are giving the full solution of linear algebra in GATE 2024 mathematics. So let us first read the question. Let A equal to 2 by 2 matrix from M to C 0 to 0 and T such that M to C to M to C with a linear transformation given by TB equal to AB. The characteristic polynomial of T is this. So just we have to find the characteristic polynomial of T. So we know that the standard basis of M to C is this 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So this is an easy work to find the matrix of T with respect to this basis, standard basis. So just find this, and this will be 4 by 4 matrix, and that will be 0 0 2 0. Just simply find the matrix representation of T with respect to this order basis beta, and this will be 0 0 2 0 0 0 0 2 2 0 0 0 0 2 0 0. Then just we have to find the characteristic polynomial of T. So if we take this as A, then we have to find that date A minus xi. So that will be this minus x 0 2 0 0 minus x 0 2 2 0 minus x 0 0 2 0 minus x. So simply find the determinant of this matrix in this way. Say minus x into this 3 by 3, that is minus x 0 2 0 minus x 0 2 0 minus x, and then 0 into some minus 0 into something, then plus 2 into this 3 by 3 determinant, that will be 0 minus x 2 2 0 0, and this is 0 2 minus x. Just find the determinant and we will get minus x into this is minus x cube plus 4x plus 2 into minus 2 x square plus 8. So finally we will get x to the power 4 minus 8 x square plus 16. So this will be the characteristic polynomial of the given operator T. So actually in question we are given that the given matrix is A. So we should not denote this matrix of T by A, just denote it another, say B, and to find date B minus xi. So this is the matrix of T, that is B, and this is the characteristic polynomial of T, x to the power 4 minus 8x square plus 16. So clearly option A is the correct option, and option B, C, D are not the correct option. So this is the solution of this problem. First we read the question. Let A belongs to M and C be a normal matrix, and the definition of normal matrix, we know that a matrix A is said to be normal if A star equal to A star A, where A star is the conjugate transpose of A. Then consider the following statements. Statement 1 says that if all the eigenvalues of A are real, then A is Hermitian, and statement 2 says that if all the eigenvalues of A have absolute value 1, then A is unitary. let us recall the definition of Hermitian and unitary matrix. A matrix, this is the definition of normal matrix. And if a matrix A, for this A, if A star equal to A, then A is called self-adjoint or Hermitian. And if for a matrix A star equal to I equal to A star A, then this matrix is called unitary A. So this is the definition of three definitions given in this question. So now first look at option 1 and let us now discuss about statement 1. Statement 1 says that if all the eigenvalues of A are real, then A is Hermitian. So we are given that all the eigenvalues of A are real. And also we are given that A is normal matrix, and there is a standard result that A is normal if and only if it is diagonalizable, and that is there exists an orthonormal basis. Sorry, no need to be orthonormal. There exists a basis. There exists a basis, say beta, equal to say v1, v2 dot dot vn, such that all the elements of beta are the eigenvectors of A. That means a matrix is normal if and only if there exists a basis consisting of eigenvectors of A. So this is a standard result. So beta consisting of eigenvectors consisting of eigenvectors of A. So we have this. Now we are also given that all the eigenvalues of A are real. And we have to now prove that A is Hermitian. So that is, we have to prove A star equal to A. That is to prove A star x equal to Ax for all x belongs to this Cn. So for this, if we can show that this A star and A coincide on this basis only, that means A star Vi equal to A Vi for all I equal to 1 to up to n, then it will be proved that A star x equal to x for all x belongs to Cn, and hence A star equal to A. Keep in mind that we are using A as a matrix as well as we can use as a linear operator, the same thing. So we are using in the context of linear operator, as the matrix is same as a linear operator. So to show A star equal to A, we just show A star Vi equal to A Vi for all I equal to 1 to up to n, nothing else. So now for this, take one I for this Vi, and we now show that A star Vi equal to A Vi. So now as this Vi belongs to beta, and beta consisting of eigenvectors of A, so Vi is an eigenvector of A. So for this there exists a scalar, say lambda I belongs to C, such that we have A Vi equal to lambda I Vi. And now we also have a result, as A is normal and A Vi equal to lambda Vi, then this Vi also will be an eigenvector of A star corresponding to the eigenvalue lambda I bar. When A is a normal matrix and Vi is an eigenvector of A, there is a standard result that Vi will also be an eigenvector of A star corresponding to the eigenvalue lambda I bar. So we need to write this result here, what we use now. As Vi is an eigenvector of A and A is normal, we have Vi is an eigenvector of A star. Sorry, Vi is an eigenvector of A corresponding to the eigenvalue lambda. It should be written here corresponding to an eigenvalue lambda I. Then this Vi is also be an eigenvector of A star corresponding to the eigenvalue lambda I bar, conjugate of lambda I. So this is the standard result. We have to use this result here. So now here, as AVI equal to lambda I Vi, so Vi is an eigenvector of A star corresponding to lambda I bar. So we can write A star Vi equal to lambda I bar Vi. And now we are given that all the eigenvalues of A are real. So here lambda I is an eigenvalue of A, and as it is real, we have lambda I Vi, and that is we also have AI Vi. So we have taken arbitrary I. So what we get? We get now A star Vi equal to A Vi for all I equal to 1 to up to n, and that will be enough to be A star equal to A, as they are same on a basis of V. So now A is Hermitian. So this option 1 is the true option. So now look at option 2. So right here 1 is true. The statement 1 is true statement. Now look at option 2. If all the eigenvalues of A have absolute value 1, then A is unitary. So for this, we prove this result. Actually, this result will also be true, this statement, and we will prove this using the same argument that we now show A star equal to I. So in order to show A star equal to I, it will be enough to show that A star A at Vi equal to I Vi, that is equal to Vi for all I equal to 1 to up to n. So we now show this, that for all I equal to 1 to up to n, A star A Vi equal to Vi. We now show this only. So for an arbitrary I, take Vi, and Vi belongs to beta. So Vi is an eigenvector of A. So we have A Vi equal to lambda I Vi for some lambda I belongs to C, as in the previous proof in 1. So now take A star from left side. So A star A Vi will be equal to A star lambda I Vi. Now this is A star A Vi equal to, this is lambda I A star Vi, as A star is linear, lambda is scalar. And also using the previous result, we have A star Vi equal to lambda I bar Vi. So this is, we have mod lambda I squared Vi. And as we are given that absolute value 1, all the eigenvalues are have absolute value 1. So this mod lambda equal to 1. So this is equal to Vi. So now we have proved these things, what we actually want to prove, that A star A Vi equal to Vi. So from this, and this holds for all I equal to 1 to up to n. So now we have this A star A and I coincides with the coincides on basis beta uh, of Cn. So A star A and I will be same. So A star A equal to I. Exactly in similar manner, we can prove that A star equal to I. So now we have A star equal to A star equal to I. So A is unitary. So now we have option 2 is true. So now look at the options. Now look at the options. See option which one of the following is correct? Option A says that both 1 and 2 are true. We now just proved that 1 and 2 both are true statements. So option A is the correct option. Now B says that 1 is true, 2 is false, which is not true because 2 is true. C says that 1 is false and 2 is true. 1 is not false, it is true. So option C is not correct. Option D says that both 1 and 2 are false. Is not true because 1 and 2 both are true. So option A is the correct option only, and B, C, D are not the correct options. This is the solution of this problem. Let us first read the question. Given a real subspace W of R4, let W part denote its orthogonal complement with respect to the standard inner product on R4. Let W1 equal to span of this element and W2 equal to span of this element be real subspaces of R4. The dimension of W1 perp intersection W2 perp over R is equal to this. So this is a numeric question. So we have to solve this question only. There is no multiple answer, multiple choice actually, option. So see that here W1 is span of this element singleton set. So clearly we have dimension W1 equal to 1 and also similarly dimension W2 equal to 1. W1, W2 both are subspaces of R4. W1 and W2 both are subspaces of R4. Now, from this given subspace W1 and W2, this is very clear that this W1 intersection W2 will be just singleton 0, that is 0 element of R4, 0, 0, 0, 0. It is very clear that if we take one element x, y, z, w belongs to this intersection, then this y will be 0 and sorry, if we take one element say x, y, z, w from this, so as this x, y, z, w belongs to w1, so we must have this y equal to z equal to 0. Both of the second and third component will be 0, and also as this belongs to W1, so we have this say this x, y, z, w equal to say some scalar multiple of this, so 1, 0, 0, minus 1, and also this will be scalar multiple of this element, say 2, 1, 0, minus 1. So from here we have x equal to c and also x equal to 2d, and also for the fourth component w will be equal to minus c, and from here w will be equal to minus d. And also as y and z will be 0, so equating from here that y equal to c into 0. Okay, so this is already 0, and also from here equating y equal to d, and also from here y equal to 0, so putting here we get d equal to 0. So from here putting this d equal to 0, we have x equal to 0, and also putting d equal to 0, we have w equal to 0. So we have now x, y, z, w all are 0. So this is done. That w1 intersection w2 equal to singleton 0. Now we can find the dimension of this subspace, that is w1 and sum of w1 and w2. We have a standard result that this will be equal to dimension w1 plus dimension w2 minus dimension w1 intersection w2, and so this will be 1 plus 1 minus 0, this is equal to 2. And also we have a result that dimension, say u, if u is a subspace of V, then dimension u plus dimension u par, that is orthogonal complement of u, that is a subspace of V, will be equal to dimension V, the whole space. So using this result, we have, as w1 plus w2 is a subspace of R4, we have dimension of the complement of this subspace, that is w1 plus w2 par, will be equal to dimension R4, that is 4 minus dimension w1 plus w2, that is 4 minus 2 equal to 2. Now we also have a standard result that w1 par intersection w2 par is actually equal to dimension w1 plus w2 par. So now we have the dimension of this subspace of is 2. So clearly dimension w par intersection dimension w2 par dimension w1 par intersection w2 par, what actually we find here, we have to find here equal to dimension w1 plus w2 par equal to 2, we have just find 2. So the dimension of w1 par intersection w2 par is 2. So this is the answer, and in this way we can solve this question. We have see here, we have used here some results without proof, because these are the standard results. See from any standard book that we have used this result, that dimension w1 plus w2 equal to dimension w1 plus w2 minus dimension w1 intersection w2. This is a result. Just mark the result what we have used here. This is a standard result we have used, and this is the standard result we have used, and this is another standard result we have used here. So using these three standard result, we have now solved this question, and the answer is 2. So this is the solution of this problem. First we read this question. Let G such that M to R be given by G A equal to trace A square. Let 0 be the 2 by 2 0 matrix. The space M to R may be identified to it R4 in the usual manner. Which one of the following is correct? Uh, there are four options. Option A says that 0 is a point of local minimum of G. Option B says that 0 is a point of local maximum of G. Option C says that 0 is a saddle point of G, and option D says that 0 is not a critical point of G. So first see how the function is defined. This function G is defined from M to R by G A equal to trace A square. So simply we can identify as given in the question that M to R is like R4 to R. So if we take a matrix A equal to say X, Y, Z, W, a 2 by 2 matrix from M to R, so that element we can see as like this X, Y, Z, W as an element of R4. So simply if we calculate what is our A square, then this will be this will be simply x square plus yz, xy plus yw, zx plus wz, and then yz plus w square. So then this trace a square will be x square plus yz plus w square, that is x square plus 2yz plus w square. So simply we can take this map from a map G from R4 to R by this G x y z w equal to like this x square plus 2yz plus w square. So now if we just simply calculate to find the critical point of G, so we need to calculate Gx, that is del G del x equal to, we have 2x, then Gy equal to, this is 2z, then Gz equal to, this is 2y, and Gw is, this is 2w. So clearly if we take 0, that is equal to 0 0 0 0, that is also like this. So then clearly we have this Gx equal to Gy equal to Gz equal to Gw at this 0, at this 0 all the values will be equal to 0. So 0 must be a critical point of G or stationary point. So we have 0 is a critical point of G. Now see, we now show that this 0 is not an extreme point. 0 is not an extreme point. So as 0 is a critical point of G, so option D is not the correct option. And also we now show that neither there is a maximum, local maximum at 0, and neither there is a local minimum at 0. So 0 will be a saddle point of G. So for this we will show that if we take any neighborhood of 0, if we take any neighborhood of 0, then we will show that if we take any, let epsilon greater than 0, then we now show that there exists a matrix say A or an element of R4 such that this GA is less than G0 with this norm A less than epsilon, that is norm A minus 0. So we have to find this A in the neighborhood of 0, and also we now show that there exists a matrix B or an element of R4 such that GB greater than 0 with this B lies here less than, say, this epsilon. So we have taken an arbitrary neighborhood of 0 and we now show that there exists some A and some B in that neighborhood such that GA less than G0 and GB less than G0. And also clearly here G0 equal to 0 because G0 equal to trace 0 square, that is trace 0 equal to 0. So we have to show that such A exists here such that GA less than 0 and such B exists there such that GB greater than 0. So for this simply we just take A equal to a matrix A 0 uh, root epsilon by 2 epsilon by 4, and this is simply minus root epsilon by 4, 0. So if we calculate simply just a square, then we will get 0 root epsilon by 2 minus root epsilon by 2, 0, 0 root epsilon by 2 minus root epsilon by 2, 0, that is equal to, this will be simply minus epsilon by 4, this is 0, this is 0, and this is simply minus epsilon by 4. So clearly we have GA equal to trace A square, that is equal to minus 2 into epsilon by 4, that is minus epsilon by 2. So clearly this is less than 0, as we have taken epsilon is greater than 0, and that is equal to our G0. And also see, if we take this norm A, so simply as an element of R4, we have this norm of this element 0 root epsilon by 2 minus root epsilon by 2, 0 equal to simply root over this epsilon by 4 plus epsilon by 4, that is epsilon by 2 root equal to root epsilon by 2. Okay, so we need to take such that this norm is less than epsilon. So simply we can take this as epsilon by 2, then it will be probably this example will solve. If we take, instead of taking this root epsilon by 4, that is root epsilon by 2, okay, then we are just taking simply epsilon by 2, then probably our purpose will be served by this. Then this will be epsilon by 2, this will be epsilon by 2, epsilon by 2 minus epsilon by 2, and then finally this will be minus epsilon square by 4. This is also minus epsilon square by 4. Then this will be 2 into minus 2 into epsilon square by 4, that is minus epsilon square by 2, that is also less than 0, done. And here the when we are calculating norm A, then this will be epsilon by 2 comma minus epsilon by 2 comma 0. So this will be epsilon square by 4 plus epsilon square by 4. So this will be epsilon square by 2. So epsilon square by 2. So this will be epsilon by root 2. So this is clearly less than epsilon because root 2 is greater than 1. So such A exists such that norm A less than epsilon, that is norm A minus 0 less than epsilon. and also GA less than G0. And similarly, we will just take matrix B equal to, say, simply just delta by 2, 0, 0, delta by 2. So then clearly we have this B square will be delta square by 4, 0, 0, delta square by 4, and clearly we have this GB equal to trace B square, that is delta square by 2, clearly greater than 0, that is equal to G0. And also when we calculate the norm of this matrix B, that is norm B minus 0 equal to norm B, that is simply take as an element of R4. This will be delta by 2 comma 0 comma 0 comma delta by 2. So this will be delta square by 4 plus delta square by 4 root over this. So this is delta square by 2 root over. So this is delta by root 2, that is, oh, extremely sorry, we have to show that norm be less than epsilon, so we don't take delta, simply we will take epsilon by 2, then it will serve our purpose. So this epsilon by 2, this is epsilon by 2, this will be epsilon square by 4, epsilon square by 4, and this GB is our trace B square, that is epsilon square by 2, done, this is greater than G0. And for calculating norm B, this is epsilon by 2, epsilon, this is, so exactly in similar manner, this is epsilon by 2, 0, 0, epsilon by 2, so this is 2 into epsilon square by 4 root over this, that is epsilon square by 2 root, so this is epsilon by root 2, this is clearly less than epsilon. So such B exists such that norm B minus 0 less than epsilon and GB greater than G0. So now we get what? We now get that in every neighborhood of 0, there are elements A and B such that GA less than G0 and GB greater than G0. So 0 is neither a local maximum nor a local minimum, and hence 0 is a saddle point of G. So option C is the correct option and option A, B are not the correct option. So here option A, B and D are not the correct options and option C is the only correct option. This is the solution of this problem. See the question first. Let this inner product denote the standard inner product on R7. Let sigma equal to V1, V2 dot V5 subset of R7 be a set of unit vectors such that inner product Vi Vj is a non-positive integer for all 1 less than equal to I not equal to j less than equal to 5. Define n sigma to be the number of pairs r comma s 1 less than equal to rs less than equal to 5 such that inner product Vr Vs not equal to 0. The maximum possible value of n sigma is equal to, what is the maximum possible value of n sigma? We have to find. The options are 9, 10, 14, 5. Actually, see, for this get question, actually the answer key is given A, that is 9. So answer key says that maximum possible value of n sigma is 9. But actually this is not the correct option here. In fact, A, B, C, D, none of these options will be correct, and we now show this by an example. So for this, we just construct such V1, V2, V3, V4, V5 elements of R7 and show that simply just on verification it will be that all such Vi Vj inner product will be non-positive integer and for that inner product Vi Vj not equal to 0, we will show that there may be 15 elements in n sigma, and that is the exact maximum possible value, because more than 15 value of n sigma cannot be happen. So for first see that how to construct such set subset of R7. So let us now take V1 equal to root 3 by 2 comma 0 comma 1 by root 12 comma 0 comma 1 by root 12 comma 0 comma 1 by root 12. See, this is an element of R7. Okay. Now let us write V2, that is minus root 3 by 2 0 1 by root 12 0 1 by root 12 0 1 by root 12. We now write V3 equal to 0 0 minus root 3 by 2 0 1 by root 8 0 1 by root 8. Then we will write V4 equal to 0 0 1 by 4 0 1 by 4 0 minus root 7 by 2 root 2, and then V5 is, we will take 0 0 0 0 minus 1 0 0. So clearly all such VI's are unit vectors. This is very clear. Just verify that for all I, this inner product Vi that is norm Vi square is equal to 1 for all I equal to 1 2 dot dot 5, and then just verify that for all such ij, this I not equal to j, for all such 1 less than equal to I not equal to j less than equal to 5, this inner product Vi Vj will be actually here less than 0. Just check. For simply, if we, for just example, if we take I equal to 1 and j equal to 2, that is inner product V1 V2, just take this inner product, and this will be minus root 3 by 2 into root 3 by 2, that is 3 by 4, plus this 1 by root 12 into 1 by root 12, that is 1 by 12, plus the same thing 1 by 12 plus the same thing 1 by 12. So this is actually minus 3 by 4 plus 3 by 12, that is 1 by 4. So this is actually minus 2 by 4, that is minus half, that is less than 0. And similarly for all such I and j, this inner product Vi Vj will be less than 0. So such Vi Vj we have taken. So this is the sigma is this V1 V2 V3 V4 V5, 5 elements which satisfies the given condition. Now just here we already have said that this inner product Vi Vj less than 0. Simply just verify this for all the other ij's. Just verify simple. So as all such Vij inner product less than 0, so simply when Vi inner product, that must be not equal to 0 because all such Vi's are non-zero, and also we have inner product Vij less than 0, so this is also not equal to 0 for I not equal to j. So for all such I and j, we have inner product Vij not equal to 0. So how many elements are there in n sigma? So n sigma contains all such pair r comma s. All such pair r comma s such that 1 less than equal to r s less than equal to 5. So this set actually contains 1 1, 2 2, 3 3, 4 4, 5 5, 1 2, 1 3, 1 4, 1 5. Then 2 3, 2 4, 2 5. Then this is 3 4, 3 5, and last is 4 5. So now we have taken all such r comma s, all such pairs r comma s such that rs varies from 1 to 5. Then see clearly this n sigma contains actually here n sigma contains actually here this is 5, then 6 7 8 9 10 11 12 13 14 15. So there are 15 elements in n sigma, and clearly we have taken all such Vij not equal to 0. So corresponding to Vij, we have taken all such Ij. We are just denoting by r comma s. So all such Vs not equal to 0 here, and uh, for this we have taken all such r comma s. So n sigma cannot contain more than 15 elements because we have taken all such r comma s where rs varies from 1 to 5. So this is the maximum possible value of this set n sigma. So here actually no option is correct, and the correct option is actually 15. So 15 is the correct option. So this is the solution of this problem. First read the question. Let Ts from R4 to R4 be two non-zero, non-identity R linear transformations. Assume T square equal to T. That is, T is nilpotent operator. Then which of the following is or are true? Option A says that T is necessarily invertible. Option B says that T and S are similar if S square equal to S and rank equal to rank S. Option C says that T and S are similar if S has only 0 and 1 as eigenvalues. Option D says that T is necessarily diagonalizable. So now see from option 1 that we are given T square equal to T, only this, and Ts are both are linear transformations, non-zero. Then option 1 says that T is necessarily invertible. So if we take simply T equal to say 1 0 0 0, then clearly T square will be equal to T. This is very easy to verify. But here clearly we have taken a diagonal matrix T. So the diagonal elements are the eigenvalues of A. So there are eigenvalues which are 0 of T. So det T must be 0. That is T is not invertible. So in general option A is not correct. Then Come to option D. T is necessarily diagonalizable. Actually, we know that every idempotent operator is diagonalizable because this is very easy to prove that. Because there are some statements which are if and only statements for diagonalizability of a linear operator. One of them is linear operator T is diagonalizable if and only if its minimal polynomial is a product of a distinct linear factors. So clearly, if T is idempotent, then we have also 0 and 1 are the only eigenvalues of T, and also we have the minimal polynomial of T will be this x into x minus 1. This will be actually as this is given in question that T is non-zero and non-identity, because empty may be x. If empty equal to only x, as we are given that 0 and 1 are the only eigenvalues of T, there are no other eigenvalues other than 0 and 1 because T is idempotent. So the minimal polynomial may be mtx equal to this, mtx equal to x, or mtx equal to x minus 1. So if mtx equal to x, then we have mtt equal to t equal to 0, that is T is 0 matrix, which is not so. And if mtx equal to x minus 1, then we have this mtt equal to t minus I0, that is T equal to I. Then T will be identity operator, which is not so. So these two options are not hold here. So mtx will be this x into x minus 1, because if we just put here empty t, then we have t square minus t, that is 0. So this x into x minus will be the least degree polynomial which annihilates a. So this mtx will be this, and which is the product of distinct linear factors. So T will be diagonalizable. So option D is the correct option. Now look at option C. See, if we take simply T and S like T equal to 1, 0, 0, 0, all the other elements are 0, and take S equal to 1, 1, 0, 0. We have taken T and S, both are diagonal matrices. So clearly here T square equal to T will satisfy, and also see we have taken S as a diagonal matrix, and also 1 and 0 are the only eigenvalues of S. So option C, the hypothesis of option C is true, that S has only 0 and 1 as eigenvalues. But here see, T and S will not be similar, because if two operators are similar, then their eigenvalues will be same. Their characteristic polynomial will be same, and hence their eigenvalues will be same. But here the eigenvalues of T will be T will be 1, 0, 0, 0. That is 0 is an eigenvalue with algebraic multiplicity 3, and here the eigenvalue of S are 1, 1, 0, 0. That is 0 is an eigenvalue of S with algebraic multiplicity 2. So if T and S are similar, then this cannot be true. So we have a matrix S such that S has only 0 and 1 eigenvalues, but T and S are not similar. So option C is not true in general. Now look at option B. T and S are similar if S square equal to S and rank T equal to rank S. So this actually this option will be true, and we now prove this result. Here this S square equal to S implies that S is also idempotent. S square equal to S, this is for option B. S square equal to S implies that S is idempotent, and 0 and 1 are the only eigenvalues of S. And also we have just proved that idempotent operator is diagonalizable. So S is diagonalizable. So there exists a basis consisting of eigenvectors such that the matrix of S with respect to this basis beta is diagonal matrix, and this diagonal elements contains 1 and 0 only. 1 and 0 only. And also we are given that rank T equal to rank S. So now first we have this T and S both are diagonalizable, and both have only eigenvalues 0 and 1. So also there exists an ordered basis gamma consisting of eigenvectors of T such that the matrix of T with respect to gamma will be this type. Only diagonal elements are there 1 and 0, and other elements will be 0. This is because these are diagonal matrix. So now we are given that rank T equal to rank S. So rank T equal to rank S means that there the non-zero rows in this matrix S and matrix T will be same. So also the 0 rows will be same. So that means this matrix of S and matrix of T will contain same number of zeros and same number of 1 in their diagonal position. So also they are 4 by 4 matrices. So as these two matrix will contain same number of 0 and same number of 1 in their diagonal position, so they must be diagonalizable because their algebraic multiplicity, their all the eigenvalues of S and T, for all the eigenvalues of, so if there are two eigenvalues of S and T, that is lambda equal to 0 and lambda equal to 1. So here algebraic multiplicity of 0, this equal to geometric multiplicity of 0, because T is diagonalizable, so eigenvalues will be regular. This will be equal to algebraic multiplicity of 0 S equal to geometric multiplicity of 0 of S, and similarly for 1. So this condition like this, say suppose 1 0 0 0, and S will be also like this, similarly say 0 0 0 1, just the positions may be same and they must be similar. So if rank S equal to rank T and S square equal to S, then T and S will be similar. So option B is the correct option. So here option A, C, D are not the correct options, and option B is the option A and C are not the correct options, and option B and D are the correct options. First read the question. Let T such that R4 to R4 be an R linear transformation such that 1 and 2 are the only eigenvalues of T. Suppose the dimensions of kernel T minus I4 and range T minus 2 I4 are 1 and 2 respectively. Which of the following is or are possible upper triangular Jordan canonical forms of T? So first see that it is given that 1 and 2 are the only eigenvalues of T, and also we are given that the dimension of kernel of T minus I4 equal to 1. So that is dimension of null space of T minus I equal to 1. So that is actually dimension of null space. We denote this as eta T minus I equal to 1, and that is actually equal to geometric multiplicity of 1 equal to 1. So this is one thing what is given in the question, and the other is that given dimension of range space of T minus 2i4 2i, that is equal to 2. That is, this is actually rank of 2 minus I equal to 2, and by rank nullity theorem we have eta T minus 2i equal to T is from R4 to R4, so this is 4 minus 2, that is 2. So this is also geometric multiplicity of 2 equal to 2. So clearly here algebraic multiplicity of 1 will be 1 or 2. 1 or 2. This cannot be more than 2 because geometric multiplicity of 2 is already 2. So this algebraic multiplicity of 1 must be less than equal to 2. So this is 1 or 2. And also algebraic multiplicity of 2 is either 2 or 3. This cannot be 4 because one eigenvalue is 1. So if we write the two cases, that case 1 is algebraic multiplicity of 1 equal to geometric multiplicity of 1 equal to 1, and then algebraic multiplicity of 2 must be 3 because algebraic multiplicity of 1 is 1, so other eigenvalue is 2, and then algebraic multiplicity of 2 must be 3 because then 3 plus 1 will be 4. So, and also geometric multiplicity of 2 is we have 2. So this is one case, and the other case is algebraic multiplicity of 1 is 2, geometric multiplicity of 1 is 1, this is fixed, and then algebraic multiplicity of 2 equal to geometric multiplicity of 2 equal to simply 3. Then this 3 plus sorry, this is 2, then this 2 plus 2 be 4. Okay, so now see, just these two cases may arise, and consider the first case. In this first case, algebraic multiplicity of 1 is 1, so 1 will appear 1 times. So in option A, that is okay, 1 appears once, and algebraic multiplicity of 2 is 3, so 3 appears 2 appears 3 times, and also geometric multiplicity of 2 is 3, so there are 2 Jordan blocks corresponding to this eigenvalue 2. There are 2 Jordan blocks. So for 1 this is okay, and there are 2 Jordan blocks corresponding to 2. So see, this is 1 Jordan block corresponding to 2, and extremely sorry, this is not a Jordan block. This is a Jordan block corresponding to 2 of size 2, and this is 1 Jordan block of size 1. So there are 2 Jordan blocks corresponding to the eigenvalue 2 and 1 Jordan block corresponding to 1. So in case 1, option A is the Jordan canonical form of A. So option A is the possible Jordan canonical form of A. It is correct option. Now look at option B. See here, this is 2 2 2 1 1, so this is a Jordan block of size 3 corresponding to 2. So this implies that for this Jordan canonical form there is only one Jordan block corresponding to 2, but we have geometric multiplicity of 2 is 2, this is fixed, so there must be 2 Jordan blocks corresponding to 2. So this option B cannot be the possible Jordan canonical form of T. Now look at option C. See here, also there is only one Jordan block corresponding to the eigenvalue 2. So this also cannot happen because we must have 2 Jordan blocks corresponding to the eigenvalue 2, but in option C there is exactly one Jordan block corresponding to 2. So option C cannot happen. Now look at option D and also look at the case 2. see here, algebraic multiplicity of 1 is 2 and geometric multiplicity of 1 is 1. So that means that there is only one Jordan block corresponding to the eigenvalue 1, and that must be of size 2. So this is this thing, that one Jordan block of size 2 corresponding to the eigenvalue 1. And for this, algebraic multiplicity of 2 is 2 and geometric multiplicity of 2 is 2. So that means there are two Jordan blocks corresponding to the eigenvalue 2. This is one Jordan block corresponding to 2, and this is one Jordan block corresponding to 2. Algebraic multiplicity of 2 is 2, so the eigenblocks will be of size 1. So this is the case. So option D can be the possible Jordan canonical form of T. So for case 1, A is the possible Jordan canonical form of T, and for case 2, D is the possible Jordan canonical form of T given in that option A and D respectively. So option B and C cannot be true here, and option A and D are the correct options. This is the solution of this problem. Let us first read the question. Let H be the subset of S3 consisting of all sigma belongs to S3 such that this hold trace A1, A2, A3 equal to trace A sigma 1, A sigma 2, A sigma 3 for all A1, A2, A3 belongs to M to C. The number of elements in H is equal to. So this is a numeric question. So we have to solve this question. So see, first if we take simply sigma equal to just, sigma is a member of S3 permutation group, symmetric group. So if we take simply sigma equal to identity element in S3, that is identity permutation. So then clearly this trace A1, A2, A3 equal to, so sigma equal to I means sigma 1 equal to 1, sigma 2 equal to 2, sigma 3 equal to 3. So then this will be trace A sigma 1, that is A1, A sigma 2, that is A2, A sigma 3, that is A3, and this holds for all A1, A2, A3 belongs to M to C. So clearly such sigma, that is sigma equal to I, must belong to this H. So H is non-empty and contains at least one element. Now see, we will just use here one result, that we know that trace A B equal to trace BA. This is a standard well known result. This thing we will use here. So first take arbitrary A1, A2, A3 belongs to M to C and start from this trace A1, A2, A3 and see what can be possible equal to this element. So this is, if we just write here A1, A2, A3, considered A1 equal to A and A2, A3 equal to B, then we will get, this is trace BA, that is A2, A3A. So this holds for all A1, A2, A3 belongs to M to C. So simply if we take sigma equal to this, that is 1, 2, 3. So 1 goes to 2, 2 goes to 3, 3 goes to 1. Then this is, we have trace A sigma 1, A sigma 2 into A sigma 3. So this holds for all A1, A2, A3 belongs to sigma, belongs to M to C for this sigma. So such sigma belongs to H. Like this sigma equal to I belongs to this H. So such sigma belongs to H. So we have another element in H. So H contains at least two elements. Now also similarly take from this trace A1, A2, A3. And now just take like A1, A2 equal to say A and A3 equal to say B. Then this will be simply, sorry, this is B, this is A3. So then this will be trace A3, A1, A2. So that means this is trace A sigma 1, A sigma 2, A sigma 3. So that means if we take sigma equal to 1, 2, 3, 3 goes to this 1 goes to 3, this 2 goes to 1, and this 3 goes to 2. That is, this is 1, 3, 2, and this is also 1, 2, 3. So like the above sigma, this sigma also is a member of H, because for this sigma, this trace A1, A2, A3 equal to trace A sigma 1, A sigma 2, A sigma 3 for all A1, A2, A3 belongs to M to C. So such sigma belongs to H. So we have these three elements in H, and clearly there does not exist another sigma such that this trace A1, A2, A3 will be equal to trace A sigma 1, A sigma 2, A sigma 3 other than this 3 sigma. Because if we try to find another such sigma, so start from trace A1, A2, A3. So there are only two options we can use this, like this A and this B, or this is A, this B. So all such options they have been just we have used and find what can be equal to with this trace A1, A2, A3. And for this we have such three sigma. One is sigma equal to Y, and the other two sigmas are here, this three cycles. So H contains only these three elements, I, 1, 2, 3, and this is 1, 3, 2. So just you take, just verify, just the other sigma cannot belong to H. Just take one sigma equal to say 1, 2, and just verify that there exists A1, A2, A3 such that this trace, if this sigma equal to 1, 2 belongs to H, then we must have this trace A1, A2, A3 equal to trace A sigma 1, that is A2, A sigma 2, that is A1, and A sigma 3, that is A3. So this thing cannot happen. For all A1, A2, A3 belongs to C, this cannot happen in general. So this H, similarly, the other sigma cannot belong to H. So only H contains only these three elements. So H contains these three elements. So this is equal to 3. So now the answer will be this numeric answer. This is actually equal to 3. The number of elements in H is equal to 3. So this is the answer, and in this way you can solve this problem. So this is the full solution of linear algebra in GATE 2024 mathematics. Thanks for watching.